Okay, let me recall what we have done. So first of all, what is the best approximation? So if V over F, where F is R or C, is an inner product space, and W is a subspace of V, and V is a vector in V, then V is said to be a vector, say W naught is said to be the best approximation by vectors in W of V if V minus W naught norm is always less or equal to the norm of W minus V or V minus W is always for every W in W. So we obtained a few other conditions also for the situation when W naught in W is the best approximation by vectors in W for a vector V in V, that the inner product is 0 of V minus V naught with every W in W, and this is if and only if. So if it is best approximation, then this inner product is 0, and if this inner product is 0, then W naught is the best approximation. We have also proved that if W naught is a best approximation to a vector V in V by vectors in W, then this is unique. And we also have obtained a categorical expression for this W naught. So if W is finite dimensional and we have an orthogonal basis for W over F, W1, W2, Wm, in that case W naught can be explicitly written in terms of Wi's, and this is the linear combination, say alpha k Wk, where the coefficient alpha k of Wk is the inner product V with Wk divided by norm of Wk square. Since Wk is a basis vector, therefore it is not 0. So norm of Wk is also not 0. So this makes perfectly sense. So before proceeding further, let me have just one or two examples on best approximation, and then we should move to something else. All right, so examples. So let's say that V be R2 over R. So V is R2, F is R. So what does it consist of? It consists of ordered pairs X, Y in R2. That means X as well as Y, both are in R. So when you are writing this as R2, you need not write inside this. This means all ordered pairs of this one. And let us take this be inner product with respect to the inner product, the standard inner product. Suppose this is B, the inner product space. With respect to the standard inner product. That means if you have two vectors, say x1, y1, so say this vector, say u is x1, y1, and say v is say x2 y2 in v. So the inner product is defined for then this inner product of u with v is x1 x2 plus y1 y2. If you define like this, the inner product, and so this makes the norm as such of this as x1 y1. So x1 minus y1 and the norm of u square will be u. So this is your x1 square plus y1 square. So if you see carefully, this is the distance between the point u, that is x1 y1, and the origin. So if you see, let us say this is here v is r2, and this is x-axis, this is y-axis. And so this is the distance of this point from the origin. This is your origin for any point x1, y1. So if you think about the norm as the distance, then they and let us take w. So take w. So let us take this okay. This is w. So w. Let us take w to be the subspace spanned by the vector say 1, 1. And let us take w be the subspace spanned by the vector 1, 1. So this means that this is x times so 1, 1 for every x in R. And this means that this is x in R. So this is a line that passes through origin and this point. So this is the W. So this is your W. Now, if we want to approximate a given point, let us say here P, and let us say this is P. P is this point, say here. ज़्यादा ही हल्का हो गया. This is the point x, y. And let us say this is the vector v. So vector v is with these coordinates. And now we see that the best approximation of v in v by a vector here in w. So what we claim is that this, if you drop a normal from here, so if you drop a normal from here, so this is the w naught. Let us say this is x naught, y naught. And this is perpendicular. So we claim that such will be the best approximation for this. Okay. So the distance of V from W naught, if the coordinates are this. So the distance of U,
Select green pen and color black.
green, yeah, or color black.
Yes, green pen, left side of the yellow.
Yeah.
Yes, in pen. Yes, sir, and black. Choose right side here, color black.
Black.
Yes.
Chalo,
Yes.
ठीक है ये.
Yes.
Okay, distance of V from W naught. Suppose W naught is the best approximation. Suppose W naught, X naught, Y naught in W is the best approximation of, let us say, V, which is the vector, so X, Y in this bivectors in W. And what is W? W is, as we have described here. So this distance can be written in terms of this. So this is V with W naught, and this is the norm of V minus W naught. Now you can see, as I have described already, that this can be seen using the formula that norm square of U is U comma U, and then you can use for the coordinates V minus W, and that gives you that this is basically the square root of X minus X naught square plus Y minus Y naught, which is the usual standard formula for distance in 2 dimensions Euclidean plane. So this is the distance, and so what we want to see is that V minus W naught is less or equal to V minus W for every W in W. So let us take that the square of this B says I, this square. So that we, so if this is minimum, then this xi is minimum, maximum. So it's better to remove the radicals and think of this xi as the square of this. So xi is the square of this means what is that? So xi is what? Xi is your x minus x naught square plus y minus y naught square. Now for minimum, this you can see is a function where is a continuous function, and therefore you can take that this so minimum of xi, so you can minimize this. The minimum of xi can be obtained by doing this dy by d of x naught as 0. So this will imply that the derivative here by to x naught, size of x minus x naught plus twice of y minus y naught. And this is 0. So this will give that twice you can cancel. So this is x plus y minus, so this is x naught plus y naught. And that will make x plus y same as x naught y naught. So you say that this is, say for example, say this is c. So that will make that y naught is c minus x naught. So here x naught when okay. So here x naught, y naught are to be determined, are variables. To be determined, because we want to know what is that vector in terms of xy. So c is a constant. V is a given vector. X and y are also constants. X naught, y naught are variables. Now, since this W naught is in W, and dimension of W is 1, as you see that this is spanned just by one vector, namely 1, 1. So, since W naught, which is X naught, Y naught, is in W, and dimension of W over F is 1. What we get is every vector here is of the form XX if it is spanned by 1, 1. And in particular, the same also will happen with this W naught. That means X naught and Y naught will be same. And W is of the form that you have same coordinates, alpha, 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 alpha in R. What we get is that X naught and Y naught are same. So basically, this is only one variable. And that is why I differentiate with respect to X naught. So what we get here is that if you substitute here, so X naught plus Y naught is same as X naught plus X naught. So this X naught plus X naught is equal to twice X naught. And this or this is same as twice of y naught. So this twice of y naught is, you can see here. So this implies that twice, so here it's this x naught is c by 2. So this is twice of x naught is y naught. X naught plus y naught is c. So y naught is equal to c minus and and this makes that twice of x naught, which is also twice of y naught, is c. That means x naught and y naught are equal and are equal to c by 2. And c is x plus y. So this is x plus y by 2. And hence you can put coordinates of w. W naught is x naught, y naught is coordinates are x plus y by 2, x plus y by 2. So this is the coordinates of this point w naught. We can verify also the given condition that this is actually the best approximation. So w naught is here what we have, x plus y by 2, x plus y by 2 in w. So best approximation, where v is xy in v. This is what we have got. We can verify also now the same thing that. So is the best approximation of v by vectors in w. So this is the is the best approximation of v by vectors in w. So for any particular v, that means, say for example, v is 1, 1. In that case, this w naught becomes 1, 1. That means point itself, because in that case, both v and w naught will be in the subspace w, and these fall on the same line. In that case, the two are equal. And if you have, say, v as something else, say 1, 2, 1, 2 will not lie on the line y is equal to x, so will be outside w. So if you take x as 1, y as 2, in that case, you can see this is the foot of the perpendicular on the line y is equal to x drawn from the point 1, 2, and the coordinates will be as we can see here. So this is 1 plus 2, that is 3 by 2, 3 by 2. So 3 by 2, 3 by 2. You can verify this is the case. So to verify, what do we have to see? What is the norm of v minus w naught? What we want to see, this should be less or equal to v minus w norm for every w in w. So we shall see what about the squares. So this square means this is the square of the norm. This is x minus so xy minus and w naught. W naught is x plus y by 2. X plus y by 2 norm square. And this is your x minus x by 2 minus y by 2. So this is x minus y by 2. So you can see that this is x minus y by 2 square plus x minus y by 2 square. X minus y by 2 square. This is same as x minus y by 2 square plus x minus y by 2 square. So this is x minus y square by 4, x minus y square by 4. When you add up, this is twice of that. So this becomes x minus y square by 2. So this is what it is. So norm when you take, so this will be the square root. So norm of v minus w naught. So w naught. This will be x minus y by root 2. Anyway, so this is what we want to show is less or equal to v minus w norm for every w in w. So again, we look at the so norm of v minus w for arbitrary w. This is a norm of x minus y and minus this is alpha. Alpha, every element here is of the form alpha, alpha. So this is same as norm square of x minus alpha. So norm of x minus alpha, x minus alpha. So you don't have x minus alpha norm square. So this is x minus alpha square plus x minus alpha square. So this is y minus coordinates are y. Y. So plus y minus alpha square. Now this you can prove that this is actually greater or equal to x minus x by 2 and y minus y by 2. So this is an easy thing that you can see that this inequality holds. And this is greater or equal to x minus y square by 2. You can simply open up the square so and then you can readjust the terms. This is for you. So that will make that this norm of V minus W naught is less or equal to norm of V minus W for every W in W. One more example if we want to see, then let us have this. Or let us go to three-dimensional now. So one more example. So let us take V to be R3 over R and make it inner product space with respect to the standard inner product. So we say R3 over R be the inner product space. To the standard inner product. So the inner product of that is for U, say x1, x2, x3, and V, say y1, y2, y3, B in V. Then the inner product of U with V is defined as x1, y1 plus x2, y2 plus x3, y3. Okay. And let us take a W B and V, let us say V be the vector here. Let us take this as simply 1, 2, 3. B in V. And W, let us take the subspace spanned by W1, where W1, let us take this is 304. Of V. So you know the elements of W, therefore, so this makes that W is of the form. The vectors will be so 3 alpha 0 4 beta. Alpha beta are real numbers. So we want to know the best approximation of V. So the best approximation of V by vectors in W. So let it be W naught. W. No, W. So this is what we want to find out. Now this W naught is so we claim that W naught equal to V W1 by norm of W1 square. W1 is the best approximation. Remember we had obtained already an expression explicitly for W naught when the subspace W was finite dimensional. So this comes from there. Only thing is that we shall verify the same thing. So what is here this? So V is 1, 2, 3. W1 is 304. That's what you need here. So this is what the calculations now you have to do. So inner product of 1, 2, 3 with the 304 here. Then norm square of W1 means 304. Norm square. This is the coefficient of 304. Now you can see standard inner product. So this is 1 into 3 plus 2 into 0 plus 3 into 4 divided by 3 square plus 0 square plus 4 square. This is the coefficient of 304. So this is your 3 plus 12 because this is 0 and this is 9 plus 16 and 304. Now this is 15 and this is 25. 304. You can divide by 5. So this is 3 by 5. 304. You can push inside. So this gives you the coordinates of W naught as 9 by 5, 0 and 12 by 5. So that is W naught is here 9 by 5, 0 and 12 by 5. This is what is W naught. You can verify, so verification also we can do. So what we want to say that the norm of V minus W naught is always less or equal to norm of V minus W for every W in W. So we calculate the square of the norm, V minus W naught norm is square, norm of 1, 2, 3 minus, this vector is 9 by 5, 0, 12 by 5 and square of this. So 1 minus 9 by 5 is your minus 4 by 5 and then this is 2 and this is 3 minus 12 by 5. So 15 minus 12 by 5. So this is 3 by 5. Square. So this is the square. So now you can see this is here. So minus 4 by 5 is square. Plus 2 square. Plus 3 by 5 is square. So this is your. So this is 16 by 25 plus 4 plus 9 by 25. So this is 25, 16 plus 9 by 25. So this is 1. And you have, so this is 1 plus 4. So that is 4. So the norm is, you will take the square root of this. So V minus W naught norm is square root of 5. Now we want to see that the norm of V minus W for any arbitrary W is always greater or equal to square root 5. Okay. So let us take W to be here. So so if W belongs to W, this was spanned by W1. W1 was 304. This. So that makes so that W is of the form. So W is of the form. So is alpha times 304. That is 3 alpha 04 alpha. This. And where alpha is in R, arbitrary. So V minus W is 1, 2, 3. This is V fixed minus W is 3 alpha, 0, 4 alpha. So this is 1 minus 3 alpha, 2, 3 minus 4 alpha. And so if I take the norm square, this is the square of, so you take this norm of V minus W with norm of V minus W, and that will give you these squares here. So this will be 1 minus 3 alpha square plus 4 and plus 3 minus 4 alpha square. Now you can see that this is simply. So 3 alpha minus 1 square and 1 minus 3 alpha square are same. And 4 alpha minus 3 square plus 4. So this is here 9 alpha square plus, so this is minus here. This is minus here 6 alpha plus 1. And you will have here plus 16 alpha square minus, so this is 24. So this is 24 alpha plus 9 and this is plus 4. So this gives you 25 alpha square minus 30 alpha and this is 14. So what is this? You can rewrite this expression by completing the squares. So this is 5 alpha minus 3 whole square. If I do, what do I get here? So this is 25 alpha square minus 2 into 5 into 3, that is 30 alpha. So that is already here. And I shall also have plus 9. So I must subtract 9 from here, plus 14. Good. So this is same as 5 alpha minus 3 square plus 5. Now, by all means, so this is greater or equal to 5, because at most this could be 0, but in that case, this is the case. So what I get is that norm of V minus W square is always greater or equal to 5. So that makes that norm of V minus W is always greater or this square root 5. Square root 5. Okay. And this makes that norm of V minus W is always greater or equal to norm of V minus W naught. So this W naught is the best approximation that we have verified. And what is W naught? 9 by 5, 0, 12 by 5. You remember that we also used one more method that was using geometry, that is the calculus of several variables. So the expression for this, that this is minimum, so the expression corresponding expression for V as 1, 2, 3 and W as alpha 3, 0, 4. The norm of V minus W square, this was 5 alpha minus 3 square plus 5. So this is minimum for alpha as 3 by 5. And this is what is actually lambda 1, 0, if you see in that expression. If you remember that proof that we gave. So that makes that W naught lambda 1 U1, where U1 is 0, 4. go through once again the proof, so you will find out that this is that. This gives that. I think just let me put this in 2 lines, better to put it. So this is this, and that implies, and so W naught is lambda 1 0 U1, where U1 was the basis vector, so this was 3 0 4, the basis vector. So that makes that W naught is 3 by 5, 3 0 4, that is 9 by 5, 0 12 by 5. So by both ways we have shown you. First, where we use the Gram-Schmidt orthogonalization and obtained an orthogonal basis and wrote the expression precisely as the linear combination of Wi's, where Wi's form the basis for WF. And we also proved using the geometry that W naught is lambda 1 0 U1, lambda 2 0 U2, and so on, lambda m 0 Um, where U1, U2, Um were basis vectors for that, where it need not be orthogonal basis. So without using the Gram-Schmidt orthogonalization also, that is method. So both ways we have obtained the best approximation. Now let us see a little more of geometry further. So you can note that so observe that for V1, 2, 3 in V, the best approximation of V, the best approximation of V by vectors in W. What was W? Spanned by 3, 0, 4. Is the vector W naught? This is what we have obtained. 9 by 5, 0, 12 by 5 in W. Good. Now this has the following geometric properties. So this has the following. You can see what are the properties. Following geometric properties. Number 1. What is W recall? So this is spanned by 304, and therefore this is of the form 304 alpha in R. So this is simply 3 alpha 0 4 alpha in R. So this is basically the line that passes through origin, and the point 3 is the line L passing through origin and the point 304. Why? Because you can check that this is the equation of this line L. So equation of the line that passes through 2 points x1, y1, z1, x2, y2, z2. So x minus x1 divided by x2 minus x1 equal to y2 minus y1 divided y minus y1 divided by y2 minus y1 equal to z minus z1 divided by z2 minus z1. You can call this ratio as say alpha. So what is the equation is x minus 0 passing through this, 3 minus 0, this is y minus 0, and then we have 0, the second coordinate. So 0 minus 0, z minus 0, 4 minus 0. And say this is alpha. So that makes x as 3 alpha, y 0, z as 4 alpha. This is the equation of the line. And this is the arbitrary point here. So that is the point P, say x, y, z on L makes that this is P of the form 3 alpha, 0, 4 alpha. So this vector, so this is the point's coordinate. If it falls on the line, then the coordinates have to be of the form 3 alpha, 0, 4 alpha. That means this is the corresponding vector will be in W. So you see that this point here, P, is with coordinates say x, y, z in L. Correspondingly, the vector x, y, z will be in W. So the point P, x, y, z, this lies on the L if and only if the corresponding the vector x, y, z belongs to W. This is what it is. So W is basically the line that passes through origin and the point 304. Orthogonal complement. What is the orthogonal complement of W? So is V, all vectors V in V, which are orthogonal to every vector in W. So V say coordinates x, y, z in V. So this is in R3. V is R3 such that 3x plus 4z is equal to 0. This is what we claim. You can prove also that this is what is the orthogonal complement. Now, what is this? This is the plane. This is the plane passing through origin and perpendicular to the line element. And perpendicular to the line L. What is the line L? Which passes through origin and the point T04. This is what it is. So you can see that here Z. So this you can see first of all this we are the line. So this line passes through origin. This is origin, and the point 304. So y coordinate is 0, and this is here somewhat 304. So this is somewhat here. So this is here point W. So okay, so this is the point. So this is the point 304 somewhere. Yeah. W1. So this is your W1. 304. And the line that passes through origin and this. So this is the line that you can see. This is the line L. And now you can see what is this plane. So this is your W, the line, and this is W. So the plane that passes through origin and is normal to this line L. That means it's a normal and the line will be parallel, so they will have the same direction ratios. So this you can see something like this. So this is your plane. So this is the orthogonal complement here of W, and this is what? This is the plane. So this is what it is. Is the plane. So 3x plus 4z is 0. 3x plus 4z equal to 0. Y is, of course, arbitrary. This is the orthogonal complement. You can see that this is. And the two together will make. Obviously, this is W. The line. So geometrically, if you want to see that the normal here and the line will coincide. So the normal will be always perpendicular to the plane, and since this line you can see, and therefore both of them will have same. So this is here the normal. Same direction ratios. So this is the orthogonal complement. So see another property. Number 3. So number I yeah. So 3. No, yeah. Yes. Yes. The point.
Sir chose the second one, the green in color.
Then
Then select the color black.
Okay. So the point W naught. W naught point, you remember this is, since we are writing the point, so let me write the coordinates for itself. So 9 by 5, and this is 0, 12 by 5. Now this is the point of intersection, you can see this is the point of intersection. Of the line L, and this line, you remember, this passes through origin and that point 304, and the plane P, the plane P was just now as I described, which passes through origin and is normal to this line, which passes through so it passes through 1, 2, 3 and is normal to the line and is normal to the line L. L, you remember the equation of this is x minus 0 by 3 minus 0 is x by 3, and y minus 0, that is y by 0 minus 0, 0, z by 4. So passing through origin and the point 304. Now, if you look at the line which passes through, now, so what I'm saying is that the line that passes through this 304 and origin, this is L. And this point W naught, this falls on this line that you can verify. And the point 1, 2, 3 also falls on this line. So in a nutshell, what happens is that this point is on the normal to the plane that passes through 1, 2, 3. And the foot of the perpendicular becomes 9 by 5, 0, 12 by 5. So if you want to write the line for the line, let us say L dash, passing through W naught. W naught is your 9 by 5, 0, 12 by 5. And V. V is 1, 2, 3. So equation of L dash will be x minus 1 by 1 minus 9 by 5, V2 minus V1 or V1 minus V2. That will give you the same thing because this is going to be the ratio, y minus 2 by 2 minus 0, and this is z minus 3 by here 3 minus 12 by 5. This is same as x minus 1 by minus 4 by 5, y minus 2 by 2, and z minus 3 by 3 by 5. Now you can see here that the product of the direction ratios here. So 3 into minus 4 by 5, 0 into 2. So This is the product of the direction ratio. So 3 into minus 4 by 5 plus 0 into 2 plus 4 into 3 by 5. So this is 0 in the middle and minus 12 by 5 plus 12 by 5. So this is 0. So that makes that the two are orthogonal. So the direction ratios of this line and the plane. So this is it. So this is giving me, the picture is now like this. So X, Y, and O. And this is your W naught. W naught is 9 by 5, 0, 12 by 5. And so let me have this line to Harithi. So line is so that passes through this point 304 and this, and now L dash also. We see what is L dash. So this is the line L, and this is same as our subspace W, defined by this, and W naught. Sorry, W1. W1 is this point W1, 304. This is W1. And this is the line. Okay. W naught. W naught is here. This is W naught. So you can see this is W naught. Okay. W naught. So this is 12 minus 12 by 5. So 9 by 5, 0, 12 by 5. 9 by 5 is less than 3, so it will be here somewhere, but it is also on the same line. So this will be W naught. This is your W naught. W naught is 9 by 5 and 0 and 12 by 5. This. And you can see now that the point V is 1, 2, 3 somewhere here. So this is normal to this line. So this is like this. Is the line L dash. L dash. And is the point 1, 2, 3. So this is the point 1, 2. This is our V. So this is our V. So this is our V. This is our V. 1, 2, 3. So this is what is this is your point naught. काम बढ़ा दिया मैंने अपने धन्यवाद हो गया. Okay. So this is what is the picture here. You can see that the plane is also I have described, and L also we have described, L dash also we have described. So we shall not be doing any more examples on the best approximation. Let me see the time. So we don't have much time, so we shall wind up here. So thank you very much for your kind attention.
Thank you, sir.